So I will start uh, about this part, the parallel computing with Python. Yeah. And so if you were on this page before 7 p.m., 7 a.m. today, so you should reload this because I included a bit more of text. Yeah. So just reload this and you will be safe. So I will talk about the parallel computing, right? But it would be ambitious to say that this will cover the whole topic. Yeah. This is another level of programming, yes, that you can add to your Python code, something that you have been doing, yes, from the beginning of this course. Yeah. And there are several tools in Python, yes, to make your code parallel. Yes, I will cover the basics. So I will talk about parallel computing, the different parallelization mechanisms in Python, how to implement the parallel algorithms in a couple of cases that I will discuss, right? And how to use the threads and workers on the HPC centers, right? So this topic is, I would say, more advanced. So you have gone from the very beginning, the first day, then you moved through more tools in Python, right? And this can be a bit more advanced, yeah, depending on your programming level, I would say. For some people, of course, uh, it's too easy. For other people, it's more complicated, but it depends on. So at the end, if you can tell me how do you feel this material is organized and what can I improve? So the content is based on the comments, right, that I have received uh, when we ran the course previously, and I have added a bit more material, right, so that all the people feel included in this section. Yeah. So first of all, just to run your code uh, in parallel mode and with the features I will discuss today, we need to do some prerequisites. And here I will mention how to do that for HPC2N. There are also similar guidelines for UPPMAX, NSC, LUNARC, and PDC. Yeah. So everything work almost in a similar manner, yes, for all the centers except for PDC, yes, for the Julia Python example, yes, with interaction in Julia Python. And this is due to the version of Julia that is installed at PDC. I would say Julia and Python is just one of the possible interactions that you can see in Python, right? And this is more specific, right? So in case that you need this kind of interaction, then you can write to the PDC support, right? But the goal of Julia and Python example was to show you that Python can interact very well with other well-established programming languages, including Julia. So then you can follow these lines and PDC. I stop at the point of making Julia available, right? So I will do this for HPC2N, as I mentioned, yes. So first of all, you load the modules for Python, and notice here the Python version that I am using, right? And then we create a environment, something that was discussed in the previous days. I already created this environment, right? Because it takes some time, the creation and also the installation of the programs. And this is called VPI in, let me see, it's not this one, and Python and course, it is here, right? So in order to activate this environment, I do a source Python course and then bin activate. So this activates a environment that I created previously. I wrote, notice that I wrote the complete path to the environment in case you were not sitting in the folder where the environment was created, right? But otherwise, you can just pick this part for the name of the environment being activated. So then I wanted to install some packages, and I can do this with pip install Numba, yes, because in the present case for the Python version that I am using, so Numba was not included, yes. I did it already, yes, it takes some time, that's why I did it already previously. Then I can check with Python if Numba is there. Interesting, it's taking some time to import Numba.
Can I ask a question?
Yes, it's important. Yes, yes, please.
Uh, are we supposed to find the prepared virtual environment somewhere in the tarball? Because I'm not finding it.
No, no, no. This part you need to create the environment.
Okay then.
Yes. Yes, and then you import Numba. You can see that it has been imported. And now I can exit this Python session. And for the MPI 4.py package, we also need to install it. Yes. But we also need to load some OpenMPI module. They can load this, right? So then, of course, well, I did it previously because it takes some time as well. So then I can check MPI 4.py, and you see that it's there. The next part was for the interaction of Julia and Python. And in the case of some centers, because this is a relatively old version of Julia, yes, we do this installation in this way. But for more recent versions of Julia, for instance, the one at NSC, yeah. So you instead install the Julia call package. Yeah. So maybe you're aware of Julia. So it's an interpreted language similar to Python, but it's a high performance, right? It allows you for fast prototyping and also is a fast good performance, right? Both in the same language. That's why I included this language as well. So this is a compatible version with Python. And then one installs this Julia package for the connector with the Python. I did it already, so I can check in Python if this was installed, Julia. And then we need to follow this step, yes, for the installation of the connector. So you see that it is trying to install a PyCall, right, which is a connector between Julia and Python. This is for the version 1.9, and now this connection between Python and Julia for more recent versions of Julia is being done in a different way. You can see that in the NSC tab. Yeah. So now it's trying to install this, and it takes some time. Yeah, so I will leave this part running. Yes, we don't need it at this point. So let me. Where's my window? So yes, well, let's start with the parallel programming part, right? So I wrote here a definition of parallel programming is a science and art of writing code that executes tasks on different computing units. And notice here the name course. This has been mentioned during this course, yes, the word course. And the key point here is that the tasks are executed simultaneously, right? There are other types of computing programming models where this word is not required, for instance, in high throughput computing, yes? And this is the keyword, yes, there's a parallel computing simultaneously. So previously, the computers in the old days, yes, they had only a single core per CPU, central processing unit, and therefore we could observe delays when we try to run several programs, right? And it took some time. This was one of the reasons. Also, the speed of the CPU, of course. But now the computers, even the PCs and laptops, contain more than one core, yes, per CPU. And here I depicted two possible architectures, yes. And this is what you can see in even in your PCs or laptops, where you have a multiple core. In this case, I am depicting just two cores, and they can share some memory, right? And this is useful, yes, for parallel programming when the cores share the memory. And also we can have another type of architecture where the cores, instead of sharing memory, yes, they exchange the data through some protocol by using a message passing. Yeah. So the programming model is different in these cases. Yes. Here, the cores take advantage of the shared address space. And here they need to send the messages like when we send letters to our colleagues or emails, and we receive back some new information. So, but currently the architectures are more complicated than pure share and pure distributed, and they can be mixed. as you can see here already, because locally some cores share some memory, but also they can exchange memory across each other through some possible protocol. This is how it looks for an old node on Kebnekaise. And here you can see that there are some cores, in this case 14, that share a memory at different levels. Here there is in one socket composed of 14 cores, and they are sharing this memory. They are also connected, and because of that, per node, all these cores can share up to 128 gigabytes. Yep. So why is important to know about this type of memories that are included in the nodes? This is because of the bandwidth. So depending on the type of memory that you are targeting, you can get a really high bandwidth, like if you are close to this memory here, which is very close to the cores. While if you go beyond that, yes, at this point, beyond the node, for node to node communications, as in this case. So in this case, the bandwidth is reduced to gigabytes per second. Yeah. So shared memory is useful because of this, yes, a high bandwidth. This is more specific. You have seen this type of architecture here that is more complex, and this can result in a non-uniform memory access, yeah, compared to the shared memory protocol, because there are different levels of in the hierarchy of the memory types. So uh, why parallel programming is needed? So imagine that you write your Python script, your machine learning model, right? But at some point, it occupies your resources on your laptop, right? Or even you were not aware of some parallel features in the libraries, or you simply coded a serial program. So you will be using basically one of these cores, right? A serial code running on one core. But this picture is similar to what has been shown previously in this course. And you see here the structure of a common HPC cluster, like the ones that we have in Sweden, where we have different computing nodes or many computing nodes. And if you make a zoom in yes, on these nodes and go to the CPU part, you will see the organization, something similar to what I showed you previously. And in order to make aware your code of this amount of resources, you need to tell the code explicitly how to use that, right? That's why you need to know the different programming protocols that are available, not only in Python, but in other languages as well. So, but parallel computing is not or adds some level of complexity to your serial code. I mentioned that at the beginning. And this can result in several issues in an HPC cluster, right? This can result in an underused usage of the resources or overused of these resources. So I put this picture here as an illustration of what can happen when one underuse a cluster. Uh, so you have seen how to set the number of cores that you want to use in a batch script, right? And this is similar to allocating some laundry. And so imagine that you allocate several laundry machines, right? And they start spinning, but then your program runs in serial mode. Yes, maybe you forgot to load the parallel libraries, or even the version that you are using is not supporting the parallel mode, and you allocate many cores, right? So you may think, because you cannot see it concretely, uh, how the resources are being used, you could end up in this situation where only one core is being used and the rest is just spinning, right? So this is underusing. Overusing, when you put many computations or more than are allowed for each resource, right? And this can also cause issues in the HPC cluster. Underusing is just in detriment of your project, because you receive some core hours per month or GPU hours per month, and if you exceed this number, then the priority of your jobs is reduced. They can still be allowed to run for most of the systems, but for instance, for some systems like the one in Finland, Lumi, they have a strict quota. So if you pass that, you cannot run your codes longer, as far as I remember, right? But in the HPC clusters that I will discuss today, the job will start, but the priority is reduced. So that's why it's important to check this optimal usage of resources. And I have mentioned this to my colleagues, right? At HPC2N and also at Chalmers, there is a tool that is called job usage. Yeah. And this is practical. Let me open this. So here is how it looks and how you can use that. Monitoring uses of resources. Here I wrote a description of how to use that. And I would like you to see this installed in other clusters, or maybe a similar tool, right? So that even users can see how the resources are being used during the running time. So you can see here that when one submits the job in the NAISS, yes, one gets a number which is called job ID. Then on the terminal, one types job usage, and with the job ID that you got from SBatch. And then one gets a URL that one can copy and paste on the local browser. And here one can see, after some minutes of collecting statistics, right? One can see how the resources, the CPUs, the memory, RAM per node, also the GPUs and the memory in the GPU are being used, and also other statistics for the operating system, right? So here, uh, for instance, if you requested 10 cores, this will mean you're 100%. If you are underusing the cluster, then you will see something below 100. And if you are overusing that, you will see that immediately, because you will see a red line passing the limit, the 100%. So that's quite useful. And I would like to see that for other clusters. But for other clusters, there are other alternatives. And in the other cases that are listed here, there is the possibility of logging to the computing nodes, which is not allowed on Kebnekaise. You cannot log in to the nodes where the scripts are being executed. But on other clusters where the login to the computing nodes is allowed, then you can use commands like top or htop to see how much of the memory and the CPUs is being used. So this is useful, as I mentioned previously, due to the underusing or overusing of the resources. So now I will show you a short demo on how to parallelize the code in Python. And this will be for a specific tool in Python. You can use other tools that I will also mention in the next example. Yeah? So here is the demo. It's very simple, but here you can get the idea of what is the parallel computing, yes, and how to apply that. So this is a simple for loop, which is language agnostic. So it has four iterations starting from 1 to 4. And then here I execute some function. And in particular, I choose the wait 1 second function because I don't want to saturate this code, yes, with more specific functions. This is just to simulate some workload, right? But you can use something more complicated. And in fact, in research projects, you will see frequently that for loops are very common, right? That's why when you have some code from research, targeting these for loops can make your code faster, right? So imagine that I execute this code in serial mode. This is serial, right? I haven't instructed the code to run in parallel mode. So it will use a single core or CPU, as in this case. So what it will do is that it will execute the wait function for 1 second, then the next wait for 1 second, the next wait for 1 second, the next wait for 1 second, and in total, it will take almost 4 seconds or more than 4 seconds, depending on the task being done by the operating system. Yeah. And if I want to parallelize this code, I will be looking for something like this. Instead of using one core, I will use the number of cores uh, equal to the number of iterations, so that one iteration is solved by one particular CPU. So in total, instead of running for 4 seconds, I will do this in approximately 1 second. But there are some limitations, and you won't see the perfect escalation in general, right? So there are some limits for this because of the overhead caused by the program, right? The tasks that are being run for the operating system, the communication time. There are several things that won't allow you to get the perfect escalation. So how to implement this function in Python? So I wrote this function called sleep.py, which simulates the wait for 1 second, right? And this is called n times. first in serial mode and then by using end processes. And I will use this module in Python for the parallelization. And there are other tools that I will also mention later on. So how to run this script? I copy this, right? And then I go to my terminal. Let me exit this thing here. So I already copied this script, right? So it is there. A good point from multiprocessing is that can get you started with the parallelization, and you don't need to install anything. Yes, this module is included in the base library of Python. So it's good to get started with that. So I pasted this here, right? It's there already. And I will explain you what this code is doing. So here I declare the number of iterations. First of all, import the module and also some performance counter, right, to get the timings and some system functions here. So here I declare the number of iterations. I will use 4, the number of processes, yes, that I will use. And notice that when we are using some parallelization or programming model, one sometimes changes the nomenclature. Yes. So because I am using multiprocessing, yeah. So the people or the developers from multiprocessing call these workers processes. Yeah. You will see later on that the cores that do something are called in a different manner. So in multiprocessing, the workers are called processes. That's why I will use 4 processes here because I have 4 iterations. So this is the Python function that will do the job in serial mode. So you can see here that is something common in Python. We have some function and then we have some loop. And this is the workload that I will use here. Yeah. And this can be the complex thing in your calculations because you can have many functions executed in the serial function or in the serial loop, right? Okay, so this is the serial function, and now I define a function called sleep with some workers, right? And then I pass some arguments, the number of iterations, the number of processes, and the process index. Yeah. So this will be a label for each process. Yeah. So here I do the workload partition. This workload partition is the total number of iterations divided by the number of processes. So the first thing when you do the parallelization of your code is that you need to change the way of thinking, right? So here I don't have any problem, right? So because it's serial, it's executing on a serial single core. But here I need to change the way of programming. Yeah? And here I need to divide somehow the workload that I have so that each core executes something. Yeah? So I divide the workload And then I need to tell the program where to start and where to finish. Yeah. So this is a trick that is commonly used. Yes. Where I use the process index, and then or the ending of the chunk that I will use is a process index plus one. So you can see here that instead of running everything, yes, in a single cool loop, I use now this range. This is relatively complex for the number of iterations, but imagine that now that I have 1 million iterations, and then this step makes more sense because I need to partition the 1 million into 4 processes. Yeah. So then you can see why this part is needed. And then for each range, for each yes range from the beginning to the end, I execute the function sleep. Yeah. So notice I partition the loop because I will execute each chunk on a different core. So then in the main function, I start with the timing. Yeah. So first I execute the serial function, and then I start timing the parallel function. So notice here that I am using the multiprocessing module and the process function. So this gets as an input the name of the function, yeah, and some arguments that are the arguments of the function. So I will go over the number of processes, right? And this will be the index, yes, that is used in this function. So then one appends the output, yes, of the processes. Start and also the processes itself. Append it to this list here. Then one starts the processes, and here we join or wait for the processes, yes, at this step. And finally, we end the counting. So how can I run this? So I go to my terminal, then I load these modules that I already loaded when I created the environment. And this is a trick that I use because this is a relatively short job. I don't need to write a batch script for this. Because of that, I can use type as run. The name of my project, in this case, is this one for this course. Here I specify the number of tasks. In this case, it's just one task. Yeah. And the number of cores, in this case, is 4 because I will use 4 cores. The time here is just 5 minutes. And here I start executing the Python script with Python and the name of the script. You can see here that the time spent in serial mode is 4 seconds, and the time in parallel mode is 1.03. And as I mentioned before, yes, you will not see the perfect scaling of this code and on any other code. So perfect is statistical is unfeasible. So some recommendations that I can give you at this point, right? Is that this is quite simple. You can see here the concept of the parallelization. So, but in general, maybe this part includes many things. So maybe here there is also another for loop over J. Then you execute something else. You have many lines of code, right? So something that you can do before going to the parallel coding is that you can uh, split, yes, or enclose the important features into functions. Yeah. So that then you know or approximately know how much your code takes on the features. So here you can see here that I had the two functions, and it's easy to time these functions. But imagine that here you have many lines of code, including the definition of variables, several loops, many functions, and you try to parallelize that. That's a nightmare. Yeah, I won't recommend that. So first of all, start with a working code. Yes, you know in this case that I know the answer, right? Because I am only timing the code. But first of all, make your code working in serial mode. Organize the code in features. Detect the features that are the time expensive parts. And then at this point, it's you can start thinking about the parallel mode. Something that I won't do is that I start with a serial code that is not working and go directly for parallelization because this will make the life very hard. So debugging in parallel mode is more difficult. So first of all, get your code in working serial, organize that, enclose the features into functions, time them, and see if that can be parallelized. So this wasn't mentioned at this point, but notice here that there is no problem if I parallelize this function, yes, over many cores because there is no data dependency between the iterations. So if I execute first the iteration two and then the iteration one, it doesn't matter, right? But for some codes, you cannot do that. Yeah. You need to have the results from the iteration one before you do the iteration two, for instance. In that case, you need to find some algorithm, if exists, yeah, if it exists, an algorithm that instead of doing that, yes, it replaces by something else which makes the iterations independent of each other. Okay, now after this demo, I will go to a relatively more realistic example, but still simplistic. And in this case, this is for the 2D integration. Uh, we need to solve this integral of the sinus function, and this is for the summation of these two variables. So the important point here is that I know already the output, which is 0. So this can help you. So because the analytic solution is known. but maybe in your code, there is no analytic solution. So the solution maybe is based on the output of the program, and that's why it's important to get the working code in serial mode. Yeah. So here we create a grid in the X and Y directions, and we divide the whole range of integration into bins, right? Because in a computer, we cannot do this integration in a continuous mode, but we need to get the bins, right? So here is what how I will code this function without any optimization. Yes. And here I start with the grid size. Yes. This is the name of the function, serial. So then I divide the whole range into n bins. And this is a variable that will help me to collect the summation, right? So if I don't do any optimization and I use the for loops, yes, I would do the following. Start with some value of x in the x direction, and then this is multiplied by the bin size, and this will do the iteration, right? So going from the middle of the interval for each iteration. And I will repeat the same for the J direction. Yes. And this variable here will allow me to collect the partial summations of the function sinus and with the argument that I showed you previously. So once these two loops are done, then I can collect the value into a variable called integral, which takes the total summation, yeah, and multiplies it by the grid size in 2 dimensions. That's why it's a square here. So then I proceed and time the function with the performance counter and report this timing. Let me copy this, and I think I've already copied it. Yeah, it's there. So then I can use the trick that I employed previously. Notice that I don't need 4 cores because this is a serial code. I will use 5 minutes. And also notice that I am now executing this script in the logging node where I am sitting here, but I send that to the Slurm queue. So this is the result. You can see the integral value, which is close to 0 within the error. Yep. And also the time spent is about 19 seconds. It can change. Yeah. So when you want to be more precise about this timing, you need to run it several times and collect the error bars. But for a single run, well, it gives you an idea of how long it takes, right? And this is basically what I did. Notice that also I use the dash C, which can be included or cannot be included. It's up to you because when you select one task, it gives you one core per task, which is dash C here, right? That's why if I don't want, I can avoid it. But if you have a more complex code, yes, like the MPI that I will mention later on, then you will need to be more strict about this dash N and dash C. Okay, so we first identify the parts of the code that are difficult or create a bottleneck. So again, this is a simplistic model, right? So maybe I have other variable declarations here, another loop that doesn't take a long time. But the important part or the bottleneck here is this thing here. Yeah? And this, well, I detected that this part can be parallelized. Okay, maybe it can run faster. And then I can go and start with the parallelization because I know that my code is giving me uh, correct results, which is close to zero. Yeah. So, but before going for the parallelization, we can try some additional optimizations also in serial mode. No, I am not jumping into the parallel code up to this point, but I will start with some possible optimizations. Yeah, and Python gives you some tools that allow you to optimize your code and see if still you can live in the serial world and get a good performance because as I mentioned before, going for the parallel mode, it creates some another level of complexity, and you need to make your code working for that. It takes time, right? Maybe you need to publish your articles within a certain time, and going for a parallelization mode is more for a long term or longer term, yes, project. So the first tool that I will show you is the Numba module. And here with some minimal efforts, you can make your code more performant. Yeah. So first, you see that I need to import the function ngit from Numba. Numba has also other functions. And I don't need to do anything else except for the fact that I need to use this decorator ngit from Numba. You can see here that the function is exactly the same and is called in the same manner, integration to this serial. So the only thing is to enclose the function, yes, by this decorator. And imagine that you have a more complex function, so maybe the decorator can work for you. It's not guaranteed, but maybe it can work. So maybe you can try that without doing any other optimization. So, okay, so then I can copy this. And let me see. And paste that in my browser. No, in my editor, sorry. exactly the same as this one. Yeah, just copy that in my directory. Then I execute the script. So instead of serial, it's called serial, but with the number decorator. And you can see here that the time was reduced, right? But actually, I expected less than that. So that could be some issue just with the nodes, right? And here you can see that approximately it was 1.9 seconds. Let me see. We'll run it. Unless, let me see if I use a different number of iterations. 10,000? No, it was the same. And in the case of the serial, yeah, it was the same. We'll make a short comparison of these two files. No, it's almost the same. Let me run it again. You can see here that, well, statistically, most likely is close to this value, 1.0, yeah. Two seconds about that, yeah. So well, there could be some fluctuations. So okay, so we can take a break now and continue in 15 minutes with the rest. Uh, we'll continue with the optimizations, right? And still in the serial mode. Yes, I haven't started with the parallel mode. Yeah, it's still in the serial mode. There are other optimizations that you can do. Yes, and uh, you know that there are already high performance programming models or programming languages like Fortran, C, C++, yeah. And the problem with these languages is that they need to be compiled, right? This is especially cumbersome when you are in the phase of developing your code. But imagine that you already know how to code in C, C++, Fortran. You don't need to modify your code frequently. It's already working. So maybe you can put the bottlenecks of your code, yes, that you detected in Python in these compiled languages, right? And these can speed up considerably the Python code. So there are several tutorials and material on how to do this for C and C++, but I didn't find at that time a lot of materials on how to combine Fortran and Python. That's why I choose Fortran, right? But the interaction with C and C++ already works as well. So in the present case, I detected that the problem or the bottleneck in the code was the integration to D, specifically the the two loops, yes, in the code. And because of that, I can write a function for this part, which is time consuming in Python. But now I write that in Fortran, yes. And this is how it looks in Fortran. This is the function name. I use this implicit known just to avoid the definition of implicit variables according to the names or the first letter in the name. Yeah. So I need to define all the variables, right? This is a good practice in Fortran. So then I start with the definition with some kind for the data, which means the precisions of the data. So then I define the grid, the integral, yes, similar to what I did in the Python code. The iterators, I, j, also the value of the interval size. These are the values for the variables in the range x, y, and also here is the cumulative variable for my sum, as I did previously. So here I divide the range, which is the pi value, and then start the summation and do the integration in two dimensions. In Fortran, we use do, not for in this case. And basically, this is the same. Yes, multiply by the grid size, and it will report and it will return the integral as an output. So, okay, I can copy this part. Yes, I copy my function, which I already did. Fortran function here. So this is basically what I have in this function. So now how to connect this Fortran function to my Python call. So the first thing is that I need to compile these functions. In contrast to the Python language, which is interpreted, in the case of Fortran, we need to compile this first to make it available. So just for the case of UPPMAX, this is the suggestion that we used, yes, to get the GCC compiler. But otherwise, if you are in the other centers, this is what worked for me. H2PyA dash C dash N. My function will be the name of the API that is returned. So you need to follow similar steps if you are connecting C and C++ and Python. So now you will see that the function is being compiled. Yeah, as you can see here. And it returns an API, which is called this name. Yeah. So as you can see here, it's the API. And this is what I can call from Python. So notice that if I change the Fortran function with some new code, I need to recompile the code. And that's why Fortran and C++ are not that good at prototyping. Yes, especially imagine that you have a very long code. Yeah. And you need to recompile. Sometimes it takes even hours, right, to compile the code. But in this case, it was short and it doesn't take a long time. Yeah. So now I need a caller, yes, for the API that we generated in Fortran. So I call this script call Fortran code, yes, which should be already here. Yeah, it's here. I specify the grid size as an input argument. So then I import the function name, yes, that was compiled, my function in this case. And here I call my function, which is the API, and the name of the function that was included there. Yeah. So basically integration to D and Fortran, and time this function. So how to run this? We can use our script. But now with the caller for Fortran. And you can see here that in this case, in this output, it gives me 1.3 seconds compared to the initial value of about 20 seconds. So this is one possibility, right? In case you know already a compiled language, yes, you can connect Python and this compiled language. And we saw the tedious step, which is the compilation. That's why I found that Julia can be also connected with Python. Julia is high performant, and also it doesn't need to be compiled, it's interpreted. But in contrast to Python, it's quite fast. So you can live inside Julia without having to learn or to use another language. So how can I program or code the integration to the function with Julia? So this is the function. So it takes an argument with an integer value. So then you get the interval size, cumulative sum, and then the two for loops that also were done in Python. And that's why I installed the connector between Python and Julia, because here we will be calling the Julia function. So notice that depending on the versions of Julia, the connection is different, and this was mentioned in the prerequisites. Specifically, you can see the difference in the NSC and HPC2N versions. So in the case of Julia, I copied this function here, which is in Julia. It's already there, yeah. And then the connector or the caller is this one for the Julia version that I am using at HPC2N. So this script, and I can run that in a similar manner as I have been doing up to this point. Interesting. Hmm. So I think I need to do this step. Previously, Julia install the connector. Let me see. Interesting. Well, I didn't expect this part. And I think that I have a issue with the py call. Yes, as I install that, I will need to refresh or yes, delete my Julia folder, I would say, because this is one situation that you can face with when you have the different versions of Julia. Yes, if you install the call connector in different versions, then it can get some issues. So I will check this part, right? Which shouldn't happen. So here you can see that previously when I tried that, I got this time, right, which is reduced. So if you are starting with a fresh Julia uh, version, right, you haven't installed anything, I would say, and you install the connector with Python, then it should work. But in this case, I will need to double check. Interesting. No, still not working. Yeah, so the problem is that I install this connector into for two Julia versions, and this caused some issues. So I will need to remove my my Julia folder, which is located in the home folder, and redo this. But if you start it, yes, with a fresh Julia version, then it should work. Yes. And this is the result that you can see here. Okay, so I will go to the parallelization part. We have seen the different optimizations up to this point. Yeah. And here we start with the Python tools for parallelizing your code. I will go briefly over the first tool, which is called threads. It's part of the threading module, which is built into Python. So you don't need to install that. It has the problem, right, that in Python, one works with the global interpreter log, also called jail, yeah, which tend to serialize the code. Yes, that's why this threading library in Python is not that useful for high computationally intensive task. But you can try the code and how it looks like. So it can work, for instance, if you are dealing with input and output files, right? And also at the same time doing some computations, but otherwise for a computational intensive task like this, you won't see any performance gain. And in this case, you can see here that even when I am using some threads, yes, the time is even a bit longer than when I was using the serial code in Python. Yeah. So notice the word threads when I am using the threading module in Python. You can also have threads when you use libraries for linear algebra like OpenBLAS, LAPACK, MKL, which provides you with some threading mechanism. Yeah. So if you're curious about what you are using or what the system administrator installed for these libraries, you can go and use, for instance, a NumPy show config, yeah, and this will list the libraries that are used for MKL, LAPACK, or OpenBLAS. So depending on the library, you can activate the threads, yes, in a different manner. For instance, for OpenBLAS, you can activate the threads with some OpenMP environment variable, right? So without doing any modification to your code, you can benefit from the parallelization that the people or the developers of these libraries did already. So this is one example. So in this case, I have a one matrix of this size, 3,000 by 3,000. And then we do the dot product and time this. But we can use different number of threads. So for instance, here on the terminal, I can write this. Yes. And then we copy this script. And you can see that it is here. And we execute the code. And in this case, you can see the result. It gives me the time of 1.14, and now it's 1.30. So but we can also change the number of threads to 2. Yeah. And because I am using 2 threads, I also need to specify this number here. And this is where the number of tasks and the cores per task is important. Yeah. And in this case, if I do this rearrangement, the time is reduced. Also reduced here, but statistically, I would say. Yeah. So we also we also use a Fortran in the previous example, right? To get some speed up. Yeah. So, but notice that Fortran or even a C, C++ can be further parallelized or can be parallelized, yeah, with some protocol. And in this case, I am showing you one way to do that. This can be also done with the C and C++, but I choose the Fortran example. I am using OpenMP, which is an MPI for shared programming, similar to what I mentioned at the beginning, for sharing the memory across the course. And here I do the splitting by using OpenMP. Yes. And if I were to compile the code, I use now an additional flag for OpenMP. And then I can use the OpenMP threads that are set with this variable, yes, to use the threads inside the Fortran function. So this is now the caller for Python, similar to what we did in the Fortran serial case. I am calling the API in this way, and then the name of the function, but now it includes the OpenMP parallelization inside the Fortran. So now how to use different number of threads? We just change the number of threads here externally with an environment variable, and then run the code, yes, with a Python caller. And you can see that the time is reduced, yes, even further than in the Fortran case. So this is another way to get a parallelization in Python. So first, you can start with the parallel libraries, yes, and then you can further parallelize the code, but in the Fortran code by using the threading mechanism. Now the distributed, and this is where I mentioned the distributed architecture at the beginning. So here we work by sending and receiving messages. And one way to do this type of parallelization in Python is by using the multiprocessing module. Yes, and you don't need to install that because it's part of the library of Python. Then we can use some array for the multiprocessing. So multiprocessing is more general, yes, than sending or receiving messages because it allows you also to share some data, yes, across the workers or the processes. And this is what we will do here. So we will share some data or some array for some number of processes, in this case 4. So this is now the function that we will use, integration to the multiprocessing. So we follow a strategy that have been mentioned several times by dividing the range of integration according to the index of the process. And then we collect the partial integrals, And finally, we join the partial integrals into some number. So here we start the processes. We use the process function for multiprocessing. So I mentioned previously how to do that. This accept a function name as an argument and also the arguments of the function itself. We append the processes in this way, and this will start the pool of processes, and then we can join the processes, collect the results, and report the results. So if we run this function now, we can see that the initial time, which was about 20 seconds, is reduced to 6 seconds approximately. So how to run these functions here? We report the time, so we can just run this. Let me see if I have this integration. It's here. So, and I will change the number of CPUs per task to 4 because I have now 4 workers. So you can see here that the time is reduced, yes, compared to the initial 20 seconds case. And this is a good module for get started into the parallelization programming, so you don't need to install anything. Yeah? So another way to do the distributed programming is by using MPI, message passing interface. And here you need to learn, yes, how to program with MPI and Python. So this is a reference from a previous course that we taught. And this is how it looks like, yeah, in the case of the MPI code. So we need to install MPI, something that we did at the beginning. So then we need to initialize the MPI runtime with different variables, the communicator, get the size of the communicator, and the ranks, yes, of the processes. This is similar to what we have done, the grid size. This is now the name of the function. And here we divide the workload, yes, according to the ranks. Yeah? And here we collect the partial summations for each rank. And then in the main function, we call the MPI function and collect the partial summations here and report the value. So you see here that you need to know how to do this MPI parallelization. Yeah? And how to run this code. Now you need to specify MPI run, yeah, and the number of processes and the Python interpreter, and then the name of the Python function. And you see that the time is reduced. For this case, I would recommend to use one of the templates that are provided here because not always this function srun works, right, on the command line. So that's why you need to use one of these templates here. So it's preferable, I would say. So here is how it looks for HPC2M, similar to what we have done up to now. We have now 4 tasks. Yeah. Then we load the modules, including the OpenMPI, and then we need to source the environment if MPI was installed in an environment, and this is the way to run the script. So UPPMAX, the instruction is similar, and PDC is here. So we use the cry Python module. And we can run that with srun and in this way. So notice here that at PDC, we are using 4 tasks, yes, and also one CPU per task. It's a bit different. So monitoring resources, I mentioned previously that this is useful, right? Because otherwise, when you are running parallel codes and you don't know what the code is doing, maybe you are overusing or underusing the resources. So this is the tool for HPC2N. Use the job usage, the job ID, and you will see the statistics after some minutes. Yes. But unfortunately, this is not present in other centers. So I mentioned this to my colleagues, and maybe this or other tool similar to this job usage will be installed on the other clusters. I have 2 exercises here, so you can read them and try them in the rest of this time. And here is basically the integration 2D. So I asked you to run that for different number of cores and see where you get an optimal number. So you can even try to use the job usage if you are at HPC2N or Chalmers, or the top command if you are at UPMAX or the other centers, and see if the memory and the number of cores are being used properly. I mean, if you get about 100% of you're using the number of cores that you requested. There is also another example that is also more advanced, I would say, and this is for a data frame. And here, a computation should be done, yes, for some of the entries, and this can be done in parallel mode. And I asked you to do some coding, but this is a challenging problem, and you can read that. And this is more useful, I would say, for uh, a research project, I would say. It's more advanced and it's also a bonus point. But try this one and let me know if you can run that, and you can change the number of cores and report the times. So let's take this last 10 minutes to do this.